Good morning. I wanted to share some work we completed at the end of 2020, improving the way we communicate real-time air quality conditions to the public. Before diving in, I first want to acknowledge the members of the Air Quality Assessment Group who helped do a lot of the work in this presentation. I especially want to acknowledge Dr. Nico Schulte, who is the primary staff member assigned to this project and was instrumental in making it a reality. First, a bit of context on the South Coast Air Quality Management District. So we're a government agency primarily responsible for regulating stationary sources in a 4-county area in Southern California. Our jurisdiction includes 17 million residents and 3 air basins. We face significant air quality problems. For example, in portions of our jurisdiction, we don't attain federal PM 2.5, ozone, and or PM 10 federal standards. Our ozone levels are particularly bad. We have the worst ozone air quality in the United States, and mainly because of our ozone levels, we exceed federal standards over 150 days per year. So we do all the regulatory monitoring in our jurisdiction, and because of that, we show it on a map. So we're aware of 2 primary methods that other agencies and ourselves use for displaying interpolated air quality index data in real time. So what I'm showing on the left is what we call the proxy method, which breaks up a jurisdiction into distinct areas and assigns a representative monitor to each one, or maybe multiple representative monitors to each one. On the right is the Air Now map, which uses an inverse distance weighted interpolation of the monitored values. So there are a few limitations with these techniques. So one is that we can't monitor everywhere, obviously, and it's not clear to people where the monitors are that are driving their air quality index. We get a lot of questions, where is the monitor that's populating the color on the map? The inverse distance weighted approach doesn't account for complex terrain, which is an issue in our region. Since these maps only use regulatory monitoring data, the public often uses multiple maps to get their current air quality, and they don't interpret the low-cost sensor data appropriately. A few regions in the proxy map may have multiple monitors for the same pollutant, and they're too large to represent events that occur at one monitor and not the other. And then an issue with another type of air quality map where you have point data on the map is that certain points may only be fed by monitors that monitor a particular pollutant. For example, there may be an area where ozone is driving the AQI, but at that point location, there's only a PM 2.5 monitor or sensor. So you look at that area, it may say good, but really ozone's driving the AQI, which is resulting in unhealthy air quality. So to address all these issues, we developed an AQI map that blends data from regulatory monitors, a chemical transport model, and low-cost sensors. So for all pollutants, the regulatory monitoring measurements drive concentrations near the monitor locations. For PM 2.5, we use the NOAA National Air Quality Forecast System CMAQ predictions and quality controlled and calibrated data from purple air sensors to help determine concentrations between monitors. For ozone, we also use the CMAQ model predictions to help shape the concentration surface. At some point in the future, we'll start integrating in low-cost ozone sensors. We apply a mathematical model to interpolate NO2 and CO between monitors. And then we also interpolate mathematically coarse PM and then add it to the PM 2.5 fields to get PM 10. Let's look at an example map. So here's a sample map from an hour this summer. Our jurisdiction is split into grid cells. The regulatory monitors are visible on the map, and then users can click any grid cell to get more details. So when you click a grid cell, you get a pop-up that looks like this. We show the AQI value, category, and dominant pollutant. And then we also show the AQI value for each pollutant and whether values are approximated or measured at that location. So we think that this adds an additional layer of transparency to the map. So you can see here, we're clicking on the San Bernardino grid cell. That grid cell monitors everything except for PM 2.5. So that value is approximated from nearby monitors, the CMAQ model predictions, and low-cost sensors in the region. So I mentioned that we use purple air data to help shape the PM 2.5 surface between regulatory monitors. The map on the right here shows how many purple air sensors we have in our jurisdiction. There's several hundred. The coverage is quite good, especially towards the coast. So how do we handle this data? So first, we use the two parallel channels and some statistical criteria to remove poorly performing sensors. Then we use a handful of co-located BAM and purple air sensors, so BAM are regulatory monitors, to calibrate the measurements and correct for relative humidity effects. The majority of the sensors are operated by the public, so we don't always trust that they're sited properly. So we have a criteria that we require at least 3 sensors in a grid cell and average them to help smooth out these local source impacts. We also deploy our own sensors, and with those, we're confident that they're sited properly, and they're also maintained and checked annually. So for those, we relax this requirement of 3 per grid cell, and we integrate in if there's just 1 per grid cell. So now the question becomes, can we trust this data? So here are the results of the calibration at the locations where we have co-located purple airs and regulatory monitors. So all but one of these are within our jurisdiction. Bakersfield is pretty close. So the uncalibrated data is on the left, the calibrated data is on the right, and you can see that the uncalibrated purple airs largely measure too high. However, the calibrated data is mostly unbiased, and we don't really see a significant spatial variation. And these monitors are in drastically different climates and environments. However, this is still low-cost sensor data. So we don't trust that 100%. So we don't force the map exactly to the measured values. And I'll show you now how we do this. So these are 2D schematics showing the concentration as a function of position on the map. So we're showing concentration residual versus position on the map. And granted, this is done in 3 dimensions when it's actually implemented. And the concentration residual is the predicted value minus the monitored value at the monitor. So with no low-cost sensors, which is the plot on the left, the model field is tied down to the regulatory monitored values. With low-cost sensors, we combine the sensor data with the model data based on their relative uncertainties. The low-cost sensors bring the concentration field closer to their measured value. It doesn't quite force it to that measured value, but it brings it closer. So basically, in between the monitors, the model and the low-cost sensor data are weighted based on their relative uncertainties and are used to shape the map. So now we can look how this technique works compared to other methods. So we've done extensive performance analysis to compare our proxy method and the inverse distance weighted approach used in AirNow. So our primary tool is leave one out cross-validation, and we do this for all pollutants. And basically, the way we do this is we remove one monitor at a time, and we calculate what the interpolated value would be at that monitor and compare it to the actual measurement. And this is done for almost a year of backwards predictions. We can do this for all monitors to calculate a root mean squared error where lower is better. So the table shows that our methodology, which we call blended, produces lower errors than both the proxy and inverse distance weighted approach for all pollutants. Since our treatment of PM 2.5 is a bit more complex, we also use several independent data sets to evaluate performance. So we have gravimetric data. So this gravimetric data isn't integrated into, we can't use it in real time, obviously. It's not integrated into the map. It's also not integrated into the NOAA model. So we're able to use this as an independent data set at 11 sites. And these are the sites that don't also have co-located continuous PM 2.5 monitors. We also use 2 relatively new continuous monitors, which were not yet integrated into the NOAA model. And from that, we find that we're more accurate at these 11 gravimetric monitoring locations and in North Hollywood. The blended approach is less accurate at Mission Viejo, but this should be resolved as the bias correction will automatically improve the NOAA model. The NOAA model is bias corrected. Okay, so we also see a few other benefits of this formulation, which are especially apparent during wildfires. So the 2 maps show what the blended map and the proxy map would look like during an hour where the Woolsey fire was producing smoke. So we recreated the data from 2018. So the purple air data and the NOAA model data can help capture localized smoke plumes that don't reach the regulatory monitors. The higher resolution better represents the wildfire plumes. And the way we have this set up is that the code automatically ingests PM2.5 data from temporary monitors. So during large smoke events, we deploy E-bands. As soon as they're cited, the code automatically picks them up and integrates them as if they were a regulatory monitor. So we find that the map performance is especially good on these wildfire days. So the table on the right shows that the blended map produces the most accurate data when looking specifically at wildfire days. So I'll push play on this map. You can see that this is what the map would look like during the Woolsey fire back in 2018. For this example, the circles represent the locations of the continuous PM2.5 monitors, not all the monitors. And the map does a good job of capturing the shape of the plume, even between our regulatory monitors. So to wrap things up, the map has been really well received by the public, and we're noticing that the public are interpreting the data correctly. The integration of the purple air data helps satisfy members of the public that want monitoring on their street, in their neighborhood. And it helps also because they have a little bit of ownership in this. So either they can get their own sensor or they look and there may already be sensors in their neighborhood. So it really helps answer the question, what's the air quality like in my neighborhood? So we've deployed this map on the South Coast AQMD homepage and also integrated it into our mobile app. Users can bookmark grid cells and name them, and the app will also push notifications when air quality is poor. We're also really focused on providing easily accessible guidance so the public knows what actions they should take for a given AQI level. And we're also now working with the Air Quality Sensor Evaluation Performance Group, AQSpec, to deploy additional sensors to help fill the map. And thanks so much for listening.